Okay, so I think the next couple of examples, just again, more practice of getting used to that notation. Keeping track of i's, keeping track of n's, and then also just being familiar again with the formulas of for the cubes. So this one says let's add this up, and we don't have to necessarily go through all of them. Let's definitely do 10 though. What does that look like? So let's see. So sigma I equals 1 to 10. I don't know if I like that color as much. Maybe I'll go a little bit darker. There we go. So then it would be like I plus 3 over 10 squared, which is 100. And again, that could be factored out. So we could really simplify this as 1/100th times I equals 1, or not times, 1/100th of I equals 1 to 10 of I plus sigma I equals 1 to 10 of 3/100ths. Because I'm just basically breaking that I over 100 and then 3 over 100. And then once you have I, the 1/100th stays here. And we know that that is 10 times 1 more, so 11 over 2 plus, and then there are 10 of these, so 30/100ths. And then you would simplify. So, you could say like, well, okay, 2 goes into 10 50 times. Sorry, 5 times. Wow, my bad. 2 goes into 10 5 times. 5 times 11 is 55. So you have 55/100ths plus 30/100ths, or 85/100ths. And you could simplify that, divide by 5. What is that? 17/20. Okay. Now, we could also do that with, let's say, 100. Let's just do that one. So at 100, again, thinking about sigma I equals 1 to 100. So then, again, it'd just be I plus 3 over 100 squared, but that could be factored out. So now you've got 1 over 10,000, right? 100 squared. Sigma I equals 1 to 100 of I, and then we could say plus sigma I equals 1 to 100 of 3 over 10,000. And then again, we could evaluate this. That's 100 times 101. 100 times 101 over 2 plus 3 over 10,000 times 100, or 300 over 10,000. And again, if you wanted to simplify that, certainly you could. We know that this is 5,050, so we'd have 5,050 over 10,000 plus 300 over 10,000, and then we'd simplify 1, 2, 3. Okay. And again, I'm not as interested in the arithmetic of simplifying those right now as much as I am in making sure you understand that notation. Okay. Now, the next example. Holy cow! So now all of a sudden we're going to let n go to infinity. And I mean, and if you think about it, that's exactly what we were doing before. First, we let n be 10, and then we let n be 100, and then we let n be 1,000. And so I guess in baby steps, we're getting larger and larger. But let's just straight out, let's go for infinity. Let's get an infinite number of these things. And so we can't really put infinity here as an upper limit. So the way we get around that is we add this part out here, like the limit as n goes to infinity of this sum. So let's leave the n alone here for a second, and that means kind of ignore this limit, and let's just see, okay, well, if you had a top number, what would that look like, right? So I know that I is my counter and n squared is a constant. So this summation, I equals 1 to n, of 4i over n squared is really like 4 over n squared times I, right? Because 4 over n squared is just a constant. As soon as we figure out what n was, that's exactly what we pulled out in front, right? We pulled those out each and every time. So as soon as we know what n is, we know what that value is. So we're going to pull that in front of the sigma, and we're still going to let the limit as n goes to infinity, because this is forming a limit definition. And just like when we did a limit definition of a derivative, we had to hold that until we took its limit. So I'm going to pull this guy out in front, right? So now it becomes the limit as n goes to infinity of 4 over n squared times, or not times, I'm sorry, of I equals 1 to n of just I. Okay, now I can actually, pun intended, I can actually write an equation for this because it's the, since they're starting at 1 going to n, it's n times n plus 1 over 2. So 4 over n squared has done nothing because this is counting i's. That's n times n plus 1 all over 2. And if I think about, like, what does this look like again in terms of like a rational function? So this is like n squared plus 1. So you get 4 times n squared, sorry, n squared plus n. So n squared plus n over 2n squared. And I mean, we could do some simplifying, or we could start to take a look at this for a second, think about, wait a minute, as we approach infinity, we just saw this chapter, right? As we approach infinity, does the top win? Does the bottom win? Or is there a tie? And since these are both quadratic, this is going to behave like a 4n squared over a 2n squared, which is basically a 2. So this expression is equal to 2. So the larger n becomes, this value becomes very, very small. So even though our sum's getting large and large and large, this fraction is getting smaller, smaller, smaller. And so they sort of are opposing forces, if I can think about that, right? And so they start to level off as a horizontal asymptote because it's a quadratic over a quadratic. And so we get this value of 2. Okay, let's look at the next one. Same idea. Again, just getting used to this notation. Remember, this expression, this expression is counting i's. So right, and I know that because my index. So anything there where there's an I, that's what it's counting. So it looks like we're counting consecutive squares. But anything that's with an n or a constant, remember that will be a constant as soon as we determine what n is. So I'm going to factor out this 3n squared. I'm going to put it into the front of my sigma, not in front of the limit, just front of the sigma. So I'm going to get the limit as n goes to infinity of 1 over 3n cubed. And then it's the summation, so it'll be times, I guess it is times the summation, I equals 1 to n of I squareds. Now, I squareds was one of our formulas from the top page. So that's n times, so it's n times n plus 1 times 2n plus 1 all over 6. So I still haven't taken a limit yet. I have this constant of 1 over 3n cubed, but this becomes n times n plus 1 times 2n plus 1 all over 6. And again, if you're wondering where that came from, that's up here, right? The sum of the first n squares is right here. N times n plus 1 times 2n plus 1 over 6. That's exactly what we had. So once I know that, think about, like, if I were to multiply all this out, which I won't, but if I were, I'd have an n plus 1, I'd have 2n plus 1. So that's a cubic function over 18, right? 6 times 3, 18n cubed. Well, as we go to infinity, you want to see who's winning. Is the top winning or is the bottom winning? And if you take a look, n times 2n, that's n cubed, that's 18n cubed. So this top is going to behave like a 2n cubed, and the bottom is going to behave like an 18n cubed. So we get 2/18, which is 1/9. Okay. And again, we're just trying to get used to this notation and get used to these symbols. Okay. Let's do one more. Again, we're counting squares. We have this extra constant here. So if I think about, I could think about distributing this 1 over n cubed into each of these, but then separating that into two summations as well. So it's the limit as n goes to infinity. So so I have this 1 over n cubed summation I equals 1 to n of just 8 minus 1 over n cubed summation I equals 1 to n of I squared. So all of that is in a limit, right? So, but I know how to add up. So for this first part, right, I know how to add up the sum of the first n constants, right? And then over here, I know how to add up the sum of the first n squareds. So I'm just going to apply those formulas. So like that part should seem like the same each and every problem. The limit as n goes to infinity of 1 over n cubed, and this would be 8n, right? That's 8 times n, minus, this is 1 over n cubed, and the sum of the first I squareds, like we saw up there, was n times n plus 1 times 2n plus 1, all over 6. And, again, thinking about the limit as n goes to infinity. So this first term, it's 8n over n cubed, which is 8 over n squared, minus, and then this one, again, thinking about it's n times n plus 1 times 2n plus 1, all over 6n cubed. So as I let n go to infinity in both terms, this first term, right, you think about that, the bottom's winning. Oops, I should probably stay consistent, go yellow. So the bottom's winning. So I know that that limit will go to 0. Here, it's a tie, cubic over cubic, so just equal the ratio. So then my limit value would equal 0 minus 2 over 6, which is negative 1/3. Okay, so again, I'm hoping that going through this exercise that we get used to that notation, that we get used to what's the I and what is its role, what's the N and what is its role, and what can be factored out and what can't be. Okay, so in the very next in the next video, what we're going to do is we're going to use this as a strategy to add up an infinite number of rectangles. So that's kind of like our goal here. Okay, very good. Like I said, if this makes sense, awesome. If not, maybe we'll go back and look at it just a few those examples again.